enjoying the conference.
He's already watching.
Yeah, he's already watching, isn't he?
Yeah,
So yes, exactly. So he'll probably be watching to make sure that everything's okay here. We'll start with on the word for our sponsors. So thanks to all of the sponsors that are supporting this event: Sky Betting and Gaming, Bruntwood, Starlight Software, JetBrains, and .js. A few sort of housekeeping things to work. So first of all, you can follow us on social media. So you can find us on Twitter at LeedsJS or on YouTube /LeedsJS, and basically everything today is going to be live streamed there, so you can catch up with anything that you've missed. You can join our mail, our code of conduct. So I'll just read this out. So LeedsJS is dedicated to providing harassment-free meetup experience for everyone, regardless of gender, sexual orientation, disability, physical appearance, body size, age, race, or religion. We do not tolerate harassment of meetup participants in any form. Sexual language and imagery is not appropriate for any meetup venue or online discussion, including talks or the Slack channel. LeedsJS members violating these rules may be sanctioned or expelled from the group at the discretion of the group's organizers. So you can find the full code of conduct at this address as well. So if anybody has would like to pitch some jobs that you might have at your companies, please feel free to do that now. If you could stand up as well if you wanted to do that. Anyone? No? No jobs? Okay, the market's gone bad then. Fair enough. So the usual prize draws. So if you would like to enter our prize draws with a chance to win either a 1-year JetBrains license or an exciting sort of ticket to the .js conference. So if you want to, I'll leave you a couple of minutes to just join this. I'll probably sort of I'll pull them up again in the break. So let's get started. So yeah, one thing as well, we don't do Q&A. So for those of you who haven't been here before, so please come and chat to the speakers after their talk. So Luke has a big blog post about the reasons behind not doing Q&A. So if you have any questions about that, please ask him. So, and our first talk will be from Katie Fenn about stop memory. Don't forget to take out the gap.
Right. Okay. Why isn't that shortcut working? Displays, arrangement, mirror. Okay. Right, so this is a completely brand new version of this talk. I've never given it before, so something inevitably is going to go wrong. Something else is inevitably going to go wrong, so we'll give it our best. Hello everyone, my name is Katie Fenn, and this talk is all about memory and garbage collection in JavaScript. So first of all, you can find me on Twitter at Katie_Fenn. That's going to be on the screen throughout the talk, so please let me know what you think of my slides disappearing.
What are you doing?
Okay, please let me know what you think of my talk on Twitter. And just in case animations and videos on big screens make you feel sick or uncomfortable, content warnings will appear in the bottom right hand side of the slides on the slide before they go. Okay, so memory is really fundamentally important to our computer programs and to our computers, and it's a finite resource. As our devices are given more and more memory throughout time, applications and operating systems discover ever more creative ways of using it up again. Like in the history of computing, we have never ever had an abundance of memory. It's always been in shortage, and you can see, like from the very beginnings of like desktop computing all the way through to modern operating systems, it's just like bigger images, bigger applications. We design and use websites. Smartphones are now the most popular way of browsing the web, and this is just a high-tech tip of the iceberg. There's up to 10 years of mobile devices that are capable of browsing the web that are still out there being used, and they have a lot less memory than maybe the brand new smartphones that we're using today have. And we're often told that memory is important. In fact, I've just told you memory is important, but the truth is that JavaScript does a really remarkable job of managing memory for us. This is my copy of JavaScript, the Definitive Guide, the Rhino book. I looked up in the index memory, and it only comes up on one page. In fact, it only comes up in one paragraph. It's mentioned once in 600 odd pages. And it says the programmer never needs to worry about the deallocation of objects. The interpreter automatically reclaims memory. So that's an awful lot of detail that's just glossed over. So how does JavaScript do this? So this talk is all about taking you behind the scenes to show you how it works. Before we can answer that, we need to answer we have to ask what memory is. So memory is used by computers. This is one of the first computers. This is Colossus at Bletchley Park that was involved in the code-breaking efforts in the war. And this was a very, very physical computer. If you wanted to reprogram this computer, you couldn't just like open up a keyboard and a monitor and reprogram it that way. You'd actually read in the code that's going to be broken by the Bletchley Park computer scientists. It took weeks to reprogram Colossus. Memory was introduced much later, memory for storing programs, that is. And these first computers were called stored program computers because you could store the actual program on memory for the first time and reprogram a computer by changing what was in memory. This is what RAM looks like inside our computers these days. We call it random access memory. It's really, really blazingly fast at accessing the data that's inside her, which is very important because our programs live there, the data that's being written to and read from is there, the operating system, absolutely everything's on RAM. And the memory itself are these little black chips on these daughter ports called DIMMs that plug into our motherboard. So that's what memory looks like. Browsers allocate this memory on our behalf. The areas of memory are called heaps. And when our page loads in the browser, JavaScript creates variable and our heaps grow in a process called allocation. And when JavaScript objects are discarded or we navigate away to other pages, the heap shrinks and memory is reclaimed in a process called deallocation. So JavaScript allocates memory for us when we declare variables. Once a variable is declared, then we can start assigning values to it and start using the memory that's allocated to us. We use the equal sign to do this, or to give it its proper name, the assignment operator. In fact, all of these operators assign to memory in some way. Some of them increment, some of them decrement, but they all assign a value from something to something. So they assign a value from the right-hand side to a memory address represented by the variable on the left. For deallocation, JavaScript uses an idea called scopes. So if the heap is a farm, then scopes are like fields. They divide up memory into manageable chunks. Scopes break memory up so we can reuse variable names and protect variables from being written to from other parts of the code that we don't want to expose them to. And when a program flow enters a new block or a new function, a new scope is created that allocates memory for new variables. In JavaScript, scopes capture variables from the outside of scopes for use on the inside. So if we have 3 functions that each declare a variable called A, B, and C, then the innermost function will have access to all of those variables. And when a function has run its course, so these functions have all been called and they've all ended, its scope ends. And variables that are only used inside those scopes aren't needed anymore. They become unreachable, and that memory can be reclaimed. Variables are only retained as long as the scope exists. And understanding scopes is the key to understanding how JavaScript uses and manages memory. And the process that JavaScript uses is called garbage collection. So that's how you control memory in JavaScript. Let's go behind the scenes to see how garbage collection in JavaScript works. JavaScript belongs to a family of languages that are garbage collected languages. This means that JavaScript does a lot of work that you don't have to. Other members of this family of languages are Java, Python, PHP. They're all garbage collected languages. I think the easiest way to explain garbage collection is to contrast it with manual memory management. This is C. It's been a long time since I've written C, so I did my best here. C is a language that's used to make lots of software tools. And it gives you a lot of authority over system resources, such as memory. So if you wanted to declare an array of 10 items, you'd use the malloc function to say, please allocate me memory for the size of 10 integers. This is an awful lot of control. Memory is freed again using the free function. This is an awful lot of control, but it's a lot of work. Can you imagine doing this every time you wanted to declare an array? It's a lot of control, but it's a lot of work. And garbage collection is designed to take care of all of this for you. So the following slides demonstrate how garbage collection works. Specifically, they are based on how Google's V8 garbage collector works that's used in Chrome and Node.js. Firefox's garbage collector is based on very similar concepts. It also has a garbage collector, as does Safari. But this is based on Chrome because Chrome has lots of white papers that I had access to, so I decided to go with V8. So the heap is organized into a layout. It's not one unified place to dump memory. It's split up into different bits that are designed for different kinds of data. It's called a generational layout with sections called the young generation and the old generation. This divides memory into areas that are for very young data and very old and long-lived data. And it optimizes the heap for different kinds of lifetimes. So the young generation is optimized for short-lived data, and it's divided into 2 semi-spaces that are both 16 binary megabytes big. And when a semi-space fills up, a garbage collection begins. V8 pauses the execution of the JavaScript engine, so your JavaScript will not be running when this part is happening. So you could experience a performance degradation. Chrome tries to make sure that doesn't happen, but it's something to think about. Objects are traced for their accessibility from the global object or from the call stack. So this is the part that finds out whether your variables are still reachable. Are they still part of a scope that is still active? Objects that are accessible are considered alive data, and anything else is considered dead. And alive objects are marked and copied to the second semi-space, and then everything that was dead is discarded. And this process then begins again. This process is incremental in V8, which means that it breaks it up into bite-sized chunks so that your JavaScript does have an opportunity to keep running. It doesn't completely lock up the JavaScript engine. This tries to make your scripts keep performing. When the when the first semi-space fills up again, the garbage collection begins again. So objects are traced for their accessibility, the JavaScript engine is paused, alive objects are marked and copied, and objects that have survived one garbage collection are then moved to the old generation. The old generation is designed for longer lived data, so the stuff that just keeps hanging around for a long time, things like settings, for example, things that are in the global object that just stay there. So this process of managing the young generation is called scavenging, and it's the responsibility of the minor garbage collector. When I say that Chrome has a garbage collector, it really has two. It's got the minor garbage collector and the major garbage collector. And the minor garbage collector is responsible for this short-lived data. This is possible. This is a really efficient process, scavenging, and it's possible thanks to something called the generational hypothesis. And that says that most variables that we create are really short-lived. The majority of them are just set up really quickly, just temporary, and then we do away with them. And this can make this process really efficient and happen really fast. So that's the role of the minor garbage collector. The other garbage collector is the major garbage collector, and it's responsible for managing longer-lived objects. And it frees longer-lived objects across the whole heap. It's not confined to the old generation, but we're going to focus on longer-lived data now. So V8 uses a heuristic to decide when to run a major garbage collection, which is a big cop-out of me saying we're not sure when it runs. Basically, it chooses when, and it's based on the size of the heap and the last time a major garbage collection happened. It works very, very similarly to the minor garbage collection. So objects are traced for their accessibility. Alive objects are marked. This process called marking, this happens concurrently with your JavaScript in the major garbage collector. This means that your JavaScript can keep running while this process is happening. This is one of the major goals of the new Orinoco garbage collector that was written for V8. It's designed to keep your JavaScript running as long as possible and try and make this process as concurrent as possible. The next part of the process is that dead objects are added to a free list, which is an index of chunks of memory that can be used for allocating new objects. So when you come around to defining a new object, then Chrome can look in the free list to find out where data can be allocated to. This process is called sweeping, and it happens off the main thread again. Again, it's concurrent. And your JavaScript can keep running while this process is happening. Finally, memory is compacted to make it more efficient. So if you remember using Windows 95 or Windows XP, you might remember defragging your computer. It's a very, very similar process where similar data is moved and the references to that memory are rewritten to make memory use more efficient. Because these references are all being moved around, JavaScript has to pause the JavaScript engine, so everything gets paused, your JavaScript stops running at this point. That process is called compacting, and it takes about 10 milliseconds, but it can take much longer depending on the size of your heap, depending on how big your web pages are. So the mark and compact garbage collection we've just seen is the domain of the major garbage collector. There's a couple of optimizations that Chrome makes, that its garbage collector makes to tune it for different kinds of memory, for different kinds of data. So there's a process called pre-tenuring, which tunes the garbage collector for when your objects have mostly long-lived data. So if all of the data that you're creating just goes straight through the young generation, ends up in the old generation, then there is an optimization for that. There's also a second optimization if incremental garbage collection so it falls back to an incremental garbage collection if the concurrent garbage collection isn't working. So I'm going to take a couple of minutes to look at WebAssembly. I'm not going to go into detail on this, but it is really exciting. And WebAssembly completely exists outside of the garbage collected world of JavaScript. So if you want to write code that isn't garbage collected, that is manually memory managed, you can do that with WebAssembly. So WebAssembly is a way of running languages that were not written in JavaScript in your web pages. And you can use a compiler to write code that's written in C or C++ or Rust inside your browser to work alongside your JavaScript. Just like this graphics demo that uses the Unreal Engine. If you've not heard of the Unreal Engine before, it's a graphics, it's a video game graphics package tool that's used by many of the most advanced video games. So you can run this. This is actually running video running in my browser. It has a bit of a low frame rate, but only because my laptop was recording this at the time. If you search for this, you should be able to run it in your laptop, and it is really, really silky smooth. So this is possible because WebAssembly applications own their own memory. This makes more efficient manually memory managed applications possible. If you want to compile, if you want access to garbage collection, then you can compile applications written in languages such as Python with their runtime environment to get access to that garbage collector. That's how a lot of garbage collected languages are compiled down to work in the browser. There is support for garbage collection, but it's in a proposal stage at the moment. So this would mean that compiled languages would not need to bundle the garbage collector anymore from their runtimes. They would be able to outsource that to the WebAssembly garbage collector, but it's at a very early stage at the moment. So I don't have time to go into WebAssembly in detail, but this is an amazing talk by Lynn Clark. I really highly recommend that you have a look at it. It's a brilliantly accessible talk. So let's have a look at actual concrete problems with memory as they manifest in your browser. The two main classes of these are called memory bloat and memory leaks. So how do you know you have a problem with memory? The big problem with this is that you don't get an error in your browser. You don't get an error in the JavaScript console when you have a problem with memory. Usually your page just crashes and you don't get anything. You don't get told. There's lots of developers out there who might have had a memory leak in their application, but they don't know about it and they don't know how to go about fixing it because of this. And sometimes this could be unresponsive JavaScript, but this also happens with memory problems. In Safari on iOS, you're using an application, and it suddenly becomes unresponsive. You try scrolling up and down. Go on, video. Find the video working. Come on. That video is not working. Come on. No, you're not going to play with me today. And I've got the beach ball. Brilliant. Okay, let's try again. No. Well, this is going well, isn't it? Keynote has crashed. Nope. Okay. Keynote's back again. No. Well, this is good, isn't it? This has never happened to me before. This is fantastic. Okay, let's quit Keynote and see if we can get it to. Okay. okay, the video is working. I'm pushing that button. This application is generating enormous amounts of data. I'm scrolling up and down, but it's slowly slowing down the browser and it's starting to become responsive. And then we get the tab at the top. How many people have seen this happen recently on websites? I'm not sure if it's just me, but this is starting to happen more and more often. And it's usually on print publication websites where they're cramming the browser full of ads. This is becoming, this is becoming a more and more widely seen site across the web, and it's kind of sad. But that's what happens when you have a terminal memory leak. So, memory bloat is making websites that are unnecessarily large for their purpose. They've got too many videos, too many fonts, too many ads, you name it. It's just all the kitchen sink inside a website. You can open the task manager inside Chrome by clicking on the menu that is in the top right. That will tell you how much memory is being used by a website. And it will break it down into the memory and the JavaScript memory used by the JavaScript heap. So you can start to piece together whether the bloat is images, whether it's videos, or whether it's JavaScript. This verge, you can't see it here, is 479 megabytes. That was 2 years ago. I think they've slimmed it down since then. So a baseline website consumes about 100 megabytes and 3 kilobytes of JavaScript. That is just the bare bones needed to put together a blank website. That is just the empty JavaScript API and an empty DOM. The Verge, I tested it again recently and it was 200 megabytes. So it's 100 megabytes over the baseline. It's still pretty bloated, but not as bad as it was 2 years ago. So that's no problem for a laptop like this that has 16 gigabytes of memory. But my phone has I think it has 4 gigabytes. And that's a 2-year-old phone. And if you go back like 5 or 6 years, those phones have like 1 gigabyte or 2 gigabytes of memory. A website that big is going to start causing problems fast for devices like that. So the next class of problems is called memory leaks. This is when JavaScript code continually adds more and more data to the heap than it discards. So the heap just continues growing in perpetuity. Leaks are caused by code mistakes that keeps code alive, so it can't be discarded. Or in other words, this is your data in your website, and this is you thinking, oh my god, my data's still alive. So this is a first for me. I'm going to try and do a live demo. So we're going to see how this goes. I'm going to, no, that's not working, okay. Sorry. This should all happen very fluently, but my key bindings aren't happening today, so I'm going to mirror displays. Open Chrome. Okay, so these are the version of my slides in Chrome. They're actually running in Chrome, that is real Chrome DevTools. I'm going to have some fun, and I'm going to trigger memory leaks in my slide deck for funsies. So let's see if we can see what happens. So I've got a button here, and it's going to run this function. This function generates a really long string, and it stores it in a global variable, which means that because the global object exists for the entire lifetime of that tab being opened in a browser, that means that data never dies off. And accidental globals is one of the big causes of memory leaks. So what I'm going to do is I'm going to open the performance monitor, and you can find it in this little menu in Chrome DevTools. Performance monitor. And this is going to show us the size of the heap, the CPU usage, and the number of DOM nodes on the page in real time. This is a tool that is fantastic. This is the sort of thing that you see in operating systems, not in websites. This is just absolutely brilliant. So I'm going to click this button. We're going to see the JavaScript heap size. Keep an eye on this. I'm going to click it now. And we can see it climbing in real time. It's just grown from size of about 20 megabytes up to 361 megabytes. This function is generating a lot of data and keeping it alive. What I'm going to do is I'm going to open the memory tab. I'm going to click on this button here, which forces a garbage collection. And if I click on that, we can see that I'm running the garbage collector, but that memory is not being freed because it's being kept alive, because it's a global object. So I'm going to refresh the page. There we go, I've refreshed the browser. And we can see that the heap has shrunk in size again. And I'm going to go to a fixed version of this code that scopes this variable to this function. So this function should be run. That data should not be needed anymore. It should die off, and we should be able to run the garbage collector and see that heap size shrink. So I'm going to click on the button again. We're going to see the size of the heap grow. And this time, I'm going to click on the garbage collector button. We should start to see it shrink. There we go. The size of the heap has just shrunk from 381 megabytes down to 25. So scoping data is really important. It tells the browser when data that you don't need anymore is not needed, and it helps it do its job properly.
Would the garbage collection have triggered eventually, or?
Yes, it will do. It's a part of this demo that I'm doing in that clearly the browser has decided that at the moment 381 megabytes of memory is probably fine. And I think it's because other than like that button running, like there's no other JavaScript running. So I think with more allocation and application that's actually doing stuff, we would have seen a garbage collection happening. So it's for the purpose of this demo, I decided to show you the manual garbage collection. So timers is also something that keep these scopes alive. So when you use set interval, you pass a callback into it that does stuff. That callback creates a new scope that allocates memory for the variables around it, so it keeps that data alive. So if I start this timer, we should see the JavaScript heap size start growing. There we go. It's increasing and increasing and increasing. And if I kept it that way, it would just keep on growing. So I'm going to stop it. Now when I stop that timer by calling this function here, it clears the interval. That means that the callback isn't used anymore, which means that that memory should be freed. So if I run the garbage collector, that should free up that memory. So the moral of this story is to clear intervals and clear timers that you're not using anymore. And that helps free up those scopes that are created. Event handlers. Event handlers are similar things. They contain callbacks that you pass into the event handler to do stuff. They also keep scopes alive that contain references to the variables around them. So if I click this button, we should see it grow every time. I'm going to pause for a second and click. Oh, that's not good. There we go. So we can see it grow every time that I click this button. And if I try and run the garbage collector, it shouldn't shrink. The moral of this story is that you should remove event handlers that aren't being used anymore, because they keep their scopes alive. So what I'm going to do, I have a global reference to this button, and I'm going to type button dot onClick equals blank string. That removes that event handler, so if I now run the garbage collection, we should see it disappear. So get rid of event handlers that you're not using anymore. What's next? This didn't work earlier, but I'm going to give it a go. Detach DOM nodes. So when you create a new DOM node in your JavaScript using document.createElement, unless those DOM nodes are actually added to the DOM and shown on page, they are literally useless. They're not doing anything. So I'm going to click this button here, which generates 10,000 DOM nodes, and we should see this shoot up. There we go. So we've got between 200,000, 400,000 DOM nodes on the page now, but they're not shown, they're just in memory. So that can be a big bloater of memory. You can try and find them by running a heap snapshot. So in the memory tab, you can take a heap snapshot, take a snapshot, and that's going to take a survey of the entire heap. And let's see if it shows us our results. Yes, excellent. So it's given us a bunch of results. We can see that there are a few items that are really bloated, that have lots of them. I'm going to search for detached. And we can see that we've got detached DOM nodes with a size of 4 million bytes, I think. I'm going to look at those. And we can see, if I click on here, we've got a couple of items here, and it tells us buttons in window, which is the name of our variable. So you can use these to find out where DOM nodes are, where detached DOM nodes are. It can tell you where the variable where the variable is, what it's called, and which scope it's in. So let's go back. Unmirrored displays. Go back to not Chrome. Let's go to Keynote. Resume. Hey, I survived. Brilliant. Okay. Summary. This is my reward for going through a live demo. Right. Memory is a finite resource. We have no API for adding hardware to other people's computers, unfortunately. So memory can only be used, freed, and reused. JavaScript manages memory on our behalf. It does a lot of work that other languages have to do manually. It's actually wonderful what it does to us. It's very performant. We're really lucky to have it. The garbage collector frees memory after it's used. Bloat is websites that are unnecessarily large for their purpose. Memory leaks are when unused memory is not freed again and it just accumulates. And use DevTools to troubleshoot and confirm your problems. They are your friend. Thank you very much. I want to give a special shout out to Matthias and the V8 Garbage Collectors team. They proofread all the notes for this site, and without their help this wouldn't have been possible. So thank you very much. I'm going to take advantage of being on stage for a second, and I'm going to show you. Come on. I've got something that I want to announce. Go away. Displays. Okay, I'm the organizer of a conference called Front End North. It's happening in Sheffield in February next year, February the 7th. Keep your eyes peeled for this website tomorrow. We're announcing our first speakers. I'm really, really excited about who we're announcing. You can follow us on at Front End North on Twitter. Please do. We're going to be announcing speakers tomorrow. I'm really excited. But other than that, I will take no more of your time. Thank you very much.